Hello, people. Good people. Hello, good people. Welcome to video number one of section 10.14, 1014 here. We are finding Taylor and Maclauren series for a function. And in conversations that we've had in class, we said that in the previous sections, we had created this thing called a Taylor polynomial or a Maclauren polynomial, if it's centered around zero, that would approximate a function, right? And so in this section, we realize that, well, if five terms of a polynomial approximate the function, well, six terms could give me a better approximation. 10 terms could give me an even closer approximation. So if I do an infinite number of terms, would I be able to get the exact answer? And that's what section 10.14 tells us, is that if a function can be represented by a power series, that power series takes on this form. But this form is the exact form that we had seen before in the Taylor polynomial. And so therefore we call this the Taylor series. So again, it depends on the condition. If the function can be represented by a power series, it will be on an open interval containing the center, then the format that it's going to take is the Taylor or Maclauren, I guess, format that we had used for those polynomials. And so in this video, we're going to do example one. Number one, we're going to hash out a Maclauren series for cosine x, and then we're going to find the interval of convergence, because that's going to tell us on which x this series actually gives me an answer that is equal to the cosine of x. So let us begin here. Can we find the Maclauren series in summation form for the following functions? Okay, so I'm going to find, I don't know, let's go maybe five derivatives, one, two, maybe even six derivatives, fourth derivative, fifth derivative, and sixth derivative. So I'm going to find six derivatives, and I'm only doing that because finding derivatives of cosine and sine are pretty straightforward, right? The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is positive sine. And then the derivative of sine is cosine. And then we begin again. Negative sine x, negative cosine x. And so I found my six derivatives. Now I'm going to evaluate each of these at the center. So they don't tell me what the center is, but I guess implicitly they do, because they tell me the Maclauren series is what I'm building, and Maclauren series and polynomials are always centered at zero. So we're going to evaluate cosine of zero, and maybe I should be more specific and say the function value at zero is cosine of zero, which is 1. The derivative at zero would be negative sine of zero, which is 0. The second derivative is negative cosine of 0, which is negative 1. And the third derivative at 0 is positive sine of 0, which is 0. Now, wait a minute. I'm noticing every other one is 0. Is that going to continue to happen? Well, yes, because now I'm back to cosine of x. So I know that the fourth derivative is 1. I know the fifth derivative, which is the same as the first derivative, is 0. And I know the sixth derivative, which is the same as the second derivative, is negative 1. So I'm noticing that every other term is a 0, starting with the first derivative. And if it's 0, then when I set up my Maclauren series, that term is going to just disappear, right? Because if I'm multiplying 0 times whatever else, it's just going to be 0. So if you don't kind of see it in your head, this is what I'm saying. R cosine x is equal to f of 0. Well, f of 0 is 1, plus f prime of 0 times x minus my center, but my center is 0, so really that's just that, plus f double prime, which is negative 1, divided by 2 factorial times x minus 0 squared, plus 0 over 3 factorial times x to the third, plus positive 1. I'm at fourth derivative here. 1 over 4 factorial times x to the fourth plus 0 times x to the 6 over 6 factorial. And again, I guess I should continue to write it this way. I'm sorry. 0 divided by 5 factorial times x to the fifth. And then the last one that I did here is the sixth derivative, which would be 1 over, I'm sorry, negative 1 over 6 factorial times x to the 6 plus, and there's going to be an infinite number of terms after that, right? But at least I got some here to kind of see a pattern. Well, exactly what we had predicted here. 0 times x is 0, so this whole thing, let me do it in a different color. This whole thing goes away. The x to the third term goes away. The x to the fifth term goes away, and I'm starting to see a pattern. It looks like every odd-powered term will zero out because the derivative is 0. So then what am I left with? So therefore, cosine x is equal to 1 minus, instead of plus a negative, I'm just going to say minus. And I want to put the x squared over 2 factorial. X squared over 2 factorial plus, this will be x to the fourth over 4 factorial. And again, I have a plus and negative, so I'm just going to say minus. And then I'm going to move this, multiply 1 times x to the 6, so minus x to the 6 over 6 factorial plus yada, yada, yada. What do I notice? Well, I notice that the Maclauren series for cosine only involves even power terms. And the setup is pretty nifty because it's just x to the even power divided by that even numbered factorial. But I also noticed there is a oscillating positive, negative pattern to it. Now, they want me to do summation form, so what we're going to do is we're going to find the nth term here. Now, to find the nth term, I'm going to say this is my 0 term, this is my first term, this is my second term, this is my third term, and so on and so forth, right? Because those other ones went away, so they're not going to appear. So let's just use what we have. So if I follow this order, 0, 1, 2, 3, what's the pattern? Well, I have x. Now, these are all even, so I should say to the 2n. Because if n is 1, I would plug in a 1. 1 times 2 is 2. If n is 2, I would plug in a 2. 2 times 2 is 4. n is 3. 3 times 2 is 6. The first term, if I plug in a 0, x to the 0 is 1. So this takes the place of what's happening in the numerator. The denominator is just that number factorial. So really it's just 2n factorial. And then I have to worry about this oscillating positive, negative pattern. And so for that, I'm going to use a negative 1, and I'm going to take it to some power. Now let's see. The first one has to be positive. The second one has to be negative. So if I were to put an n here, and I were to substitute 0, negative 1 to the 0, that'd be positive. But if I plug in 1 in here, negative 1 to the 1, that'd be negative. If I plug in 2, negative 1 squared, that'd be positive. Okay, so I think this is the pattern that I need. Now remember, this is what we call the nth term. Some people call it the general term. And the general term tells me the pattern of the terms in my series. So this is a formula that creates the pattern. That's different than over here. These are the formulas that create the derivatives, but this formula creates the pattern. Why do I need that? Because now I can write it as a summation and say sigma starting at 0 going to infinity of negative 1 to the n times x to the 2n divided by 2n factorial. This is the power series for cosine x. Specifically, it's the Maclauren series, and we're about to test what the interval of convergence is for this series. So cosine x can be written as this expanded set of terms that I'm adding, subtracting, and it can also be written in sigma notation and summation form using the nth term as the pattern that creates each of these terms. This is a pretty big deal, because what we're saying is Cosine x, which is a transcendental function, it's a trigonometric function, a function that doesn't abide by the rules of algebra. We can make it into an algebraic polynomial that has terms that I'm subtracting, I'm multiplying, I'm adding, and this abides by the rules of algebra. Okay, so now let's check the interval of convergence. So we're going to do the ratio test. The ratio test says take the limit as n approaches infinity of the n plus 1th term, x to the 2. Now be careful here. This will be n plus 1 in parentheses all over 2 times n plus 1 factorial divided by the original function, but the original function, since it's a fraction, I'm going to multiply by the reciprocal, and I get this. The only way this is going to work is if it's less than 1, then I know what it's going to converge to. But let's continue. I can cancel this negative 1 to, I can reduce the negative 1 to the n with negative 1 to the n, and I'm only left with negative 1 to the 1. I can reduce this x to the 2n with this x to the 2n, but be careful, this is really 2n plus 2, so when I reduce, that'll be this, but I still have x squared. And then if you multiply this out, this is really 2n plus 2 factorial. So I can cancel this whole 2n factorial with all except 2n plus 2 times 2n plus 1, and then the next one would be plus 2n plus 2, and then that's where everything cancels. So I think that's what I have left. So just to rewrite this and make it look cleaner, this is the limit as n approaches infinity of, well, the absolute value is going to get rid of this, right? Absolute value of negative 1 to the 1, that's just positive, so I don't have to worry about that. On the in the numerator, I'm left with x squared. In the denominator, I'm left with 2n plus 2 times 2n plus 1. But if I'm taking the limit as n approaches infinity, that means the denominator is growing without bound, the numerator is staying the same, or at least it's not affected by n, and therefore this whole fraction, because n approaches infinity, that means the denominator approaches infinity, and if it approaches infinity, that means this goes to 0. And that's less than 1. So when is 0 less than 1? Always. So my interval of convergence is all real numbers from negative infinity to positive infinity, all real numbers, which means my radius is infinity. What this means is that this Taylor's, or in this case, Maclauren series that we created is equal to cosine x for all real numbers. I can pick any x value that I want to find for cosine. If I want to find cosine of 3.5, if I substitute a 3.5 wherever I see an x in this series, I can find the exact value if I add all the terms that go infinitely out. But even better, I can approximate it if I just use a couple of terms and substitute 3.5, 3.5, 3.5 wherever I see an x. I can get a pretty good estimate for cosine x. In the next videos, we're going to do some more, but really the idea is we're going to have to memorize that some functions like cosine x have a partner Maclauren series or Taylor series that we can use. And if you memorize those key ones, it's going to make your life a lot easier.